Hi, my name is Amirali Borumand and I'm a PhD student at Carnegie Mellon University. Today, I'll be talking about my work mitigating data movement bottlenecks in Google Workloads for consumer devices. Consumer devices like tablets and smartphones are now everywhere and used by billions of people. But one of the major issues with these devices is battery limitation, which makes the energy consumption a critical concern for consumer devices. So in this work, we take a look at the widely used Google consumer workloads to figure out the major sources of energy consumption. We look at Google Chrome web browser, we take a look at TensorFlow, which is Google's machine learning framework, and we also take a look at two other video-related workloads, video playback and video capture, that both rely on Google's video codec technology. Throughout our analysis, we make a key observation that out of all different sources of energy consumption, data movement is a major contributor. In fact, we observe that around 62% of the total system energy goes to the data movement. So one way to reduce this cost is to move computation closer to the data, or in other words, do processing in memory. But the challenge here is that these devices are extremely limited in terms of area and energy budget, and as a result, any additional logic could translate into a significant cost. So to figure out if we can use processing in memory, we dig deeper into our analysis and we make another key observation that the majority of data movement comes from simple functions and primitives. We find that we can implement these simple functions in memory using either a small embedded low-power core or a group of small fixed function accelerators. Our analysis shows that offloading these functions to PIM logic could significantly reduce the data movement, and it can reduce the energy on average by 55% and improves performance by 54%. So our goals in this work is to first understand the data movement bottleneck in modern consumer workloads, and then we want to figure out if we can use processing in memory to reduce the data movement cost. And finally, because these devices are limited in terms of area and energy budget, we want to figure out what kind of PIM logic can maximize energy efficiency at minimum possible cost. So now let me give you a little bit background on processing in memory. So PIM, processing in memory, or PIM, is a potential solution that we can use to reduce the data movement. And its idea is pretty simple. We want to move computation closer to the data rather than bringing the data all the way to the computation units. And this simple idea could provide us a couple of benefits. First, we can get rid of a significant portion of data movement. Second, we can benefit from the huge available bandwidth inside the memory. And finally, we can access the data much faster. And this whole idea has been enabled by the recent advancement in 3D stack technology that enables us to stack DRAM layers on top of a logic layer and interconnect them together using through silicon vias or TSVs. Because of the density of these TSVs, the amount of bandwidth available within this structure is much more than the bandwidth available to the off-chip CPU. So now let me talk about our analysis methodology. We did all of our analysis on a Chromebook with an Intel SoC, and we extensively used performance counter within the SoC to drive our experiments. We modeled the energy as the sum of the energy that takes place within the CPU, on-chip caches, interconnects, and the DRAM. And during our experiments, we turn off the Wi-Fi and set the display brightness to the lowest so we can make sure that the majority of the energy goes to the SoC or the memory system. During our analysis for each workload, we consider two types of PIM logic implementation, either a general purpose PIM core or a small fixed function PIM accelerator. So our PIM core is basically a customized embedded core that is designed based on the characteristics of the candidates that we find in each workload. And I'm going to talk about those candidates in this talk. So it's basically a simple embedded core that doesn't have any aggressive instruction level parallelism techniques. And it also has the SIMD units so it can benefit from parallelism. Our PIM accelerator is a small fixed function accelerator that has an in-memory logic unit, which is designed based on the characteristic of each of those candidates. Each of these accelerator has multiple copies of these units, so it can benefit from parallelism. So now let me talk about our first workload, the Chrome browser. Before I jump into our analysis, let me give you a little background on how Chrome renders a web page. So it has three major parts, and Chrome starts by downloading and parsing the source file to extract the content of the web page. And then it goes on to calculate the visual elements and position of each object. So at the end of the layout section, it knows where to draw each object and what are the visual elements. And then the final major part is about painting. The Chrome uses rasterization to paint those objects and then generates the bitmaps. And then those bitmaps are then sent to the GPU to do the compositing, which basically assembles all of those layers into one final screen image. And that's pretty much an overview of how Chrome renders a web page. But from user's perspective, the browser must provide a way to quickly load different pages, smoothly scroll those pages, and provide user with a way to quickly navigate between different browser tabs. And because of that, in this work, we focus on two important user interactions with the browser: the page scrolling and tab switching. And note that each of those includes the page loading. So let me start with the scrolling. When user scrolls a web page, it triggers three operations in the browser. It forces the browser to recompute the layout because the position of the object has changed. The browser has to do the rasterization again because the content of the page has changed. And it also has to do the compositing because there are some new objects on the display. There are some new objects that needs to be displayed. And in addition to that, there are two other important functions that I want to talk about here that play an important role into our analysis. The first one is texture tiling. Texture tiling happens between the rasterization and compositing, and its goal is to minimize the cache misses during compositing. So basically, the graphics driver invokes this function to reorganize the bitmaps before sending them to the GPU. And that's how texture tiling comes to the play. The second function is color blitting, and it happens during the rasterization. The rasterization invokes this function to convert the basic primitives like lines and text into bitmaps, and that's how color blitting comes to the play. So here I'm showing you the energy breakdown across different web pages when a user scrolls during the scrolling. This figure shows us how much each of what function in the browser consumed the most energy during scrolling. What we observed from this figure was that on average, around 42% of the scrolling energy goes to texture tiling and color blitting, the same two functions that I just talked about in the previous slides. And the rest of the energy goes to a variety of library call and function calls that each of them takes less than 1% of the total system energy. And because of that, I just labeled them here as other. So the question that we want to ask here is that where exactly in the system the energy is spent. Here I'm showing you the energy breakdown across different hardware components when a user scrolls a Google Docs web page. On the x-axis, I'm showing you how much energy goes to different hardware components like DRAM or caches, and on the y-axis, I'm showing you the total energy. What we can observe from this figure is that a significant portion of energy goes to accessing data from DRAM or caches or transferring data over the interconnect. In fact, we find that around 77% of the total energy goes to the data movement, and when we dig deeper, we figure out a significant portion of that comes from texture tiling and color blitting. Here, I'm showing you how much each of those functions spend on data movement and computation in terms of energy. As you can see from this figure, both of these functions are extremely data intensive, and the data movement generated by these two accounts for around 37% of the total system energy. So now the question we want to ask is, can we use PIM to reduce the data movement costs for these two functions? To answer that, we need to dig deeper into each of those. Here, I'm showing you the detailed interaction between the CPU and memory when texture tiling happens. As we said, the CPU does the rasterization and stores the bitmaps in memory, and then it goes on to invoke the compositing. Texture tiling happens in between. It basically reads the bitmaps, converts it to a more cache-friendly format for the GPU, and then writes them back to a location that GPU can access it. And that's where a lot of data movement happens. The majority of that data movement happens because this process has poor data locality, and also the bitmap sizes are so large that in some cases they don't even fit into the last level cache. So now let's take a look at what would happen if we move this process to the PIM. In that case, the PIM logic goes and reads the bitmaps from memory, do the conversion in memory, and then write them back to a location that GPU can access it. And in this way, it can significantly reduce the data movement, and it can also let the CPU do some other tasks while PIM is handling the texture tiling in the back in memory. So we can conclude that this function could significantly benefit from PIM execution. The only question that is left is, can we actually implement this function in PIM logic given the constraint that we talk about in consumer devices? So to answer that, we dig deeper into the texture tiling and we figure out that it only requires simple primitives. It requires memcopy, bitwise operations, and simple arithmetic operation. And as a result, we can run it at our PIM core at high performance, or we can design a simple fixed function accelerator to implement these operations. Our analysis shows that neither of these two designs takes more than 10% of the available area for the PIM logic, and as a result, both of them are feasible to implement the in-memory texture tiling. So we did the same analysis for color blitting, and I'm just giving you the key points here. As we observed, color blitting generates a lot of data movement, and that data movement accounts for around 19% of the total system energy across when user scrolls different web pages. And as a result, we concluded that the color blitting can significantly benefit from PIM execution. When we dig deeper into the function, we figure out that it only requires memset, simple arithmetic, and shift operation. And as a result, we can conclude that it's feasible to implement this function in both PIM core and the PIM accelerator. So here I want to wrap up what we find for scrolling. So we found that there are two functions, texture tiling and color blitting, that account for a significant portion of energy during scrolling different web pages in Chrome, and both of them are extremely data intensive. We find that both of them can significantly benefit from PIM execution, and because they have simple operation, it's feasible to implement them at PIM logic. So now let's take a look at the other important interaction with the browser, which is tab switching. Chrome uses a multi-process architecture. It means that each tab has its own separate process. And as a result, during tab switching, the main operation is context switch to another tab and load the content of the new page. For Chrome, the primary concern during tab switching is how fast it can load the page and make it interactive for the user, and more importantly, the memory consumption. So to reduce the tab's memory footprint, Chrome uses compression. It basically uses compression to compress the inactive tabs and then put them into a DRAM-based pool, which is called ZRAM. Whenever user accesses those tabs, the Chrome reads the data from ZRAM and decompresses them. And in that way, it can get rid of the expensive accesses to the disk. So we want to figure out and study the data movement during tab switching. And to do that, we basically emulate a user that switched between different 50 tabs. And during this experiment, we monitor the amount of data that moved between the CPU and the ZRAM. We make two key observations from this experiment. The first one is that both compression and decompression contribute to around 18% of the total system energy. And the second one is that around 19 gigabyte of data gets moved between CPU and ZRAM when user navigate through these tabs. That's a lot of data movement, and we want to figure out if we can use PIM to reduce that. So here I'm showing you detailed interaction between CPU and memory when CPU wants to swap out n pages to the ZRAM. In that case, the CPU goes and reads all of those pages, compresses them, and then writes them back to the ZRAM, and that's where a lot of data movement happens. So if we want to move this to PIM, what would happen is that the CPU would inform the PIM logic about this swap process. The PIM goes and reads those pages, compresses them, and then write them back to the ZRAM. And in this way, it could significantly reduce the off-chip data movement and it could also let the CPU do some other task while PIM is handling the compression in the background. Our analysis shows that the compression algorithm used by Chrome is simple enough that both PIM core and PIM accelerator are feasible to implement that in the PIM logic. So to wrap up the tab switching, we find out that when Chrome when users do the tab switching, Chrome tries to compress the tabs and decompresses them to reduce the tab's memory footprint. And that's where a lot of data movement happens. We find that both of the functions, compression and decompression, can significantly benefit from PIM execution, and they are simple enough to be implemented at the PIM logic. So we did the same analysis for all other workloads. I'll just give you a brief summary here. So we take a look at TensorFlow. We basically analyze the inference energy consumption across different neural networks. And we find that the majority of the inference energy goes to the data movement. When we dig deeper, we find that the majority of that data movement comes from two functions, packing and quantization. Packing is just a simple function that tries to reorder the element of the matrices to minimize the cache misses. It accounts for up to 40% of the inference energy, and it generates a lot of data movement. And when you look at the function, you figure out that it's a simple data reorganization process that only requires simple arithmetic. Quantization, on the other hand, is trying to convert floating points into integers to improve inference execution time and energy consumption. It accounts for up to 16% of the inference energy, and it also generates a lot of data movement. And when you look at the function, when you look deeper into the function, you figure out that it's a simple data conversion operation that only requires shift, addition, and multiplication. Based on our analysis, we conclude that both of these two functions can significantly benefit from PIM, and because they are simple, they have simple operations, it is feasible to implement them in the PIM logic. So we did the same analysis for the two other video-related workloads. We take a look at the VP9 decoder and analyze the energy consumption when it's used to play back a 4K Netflix film. And we also take a look at the VP9 encoder and analyze the energy consumption when it's used to do the real-time encoding of an HD video. So we find that, like the two other workloads, the majority of the energy goes to the data movement, and the majority of that data movement comes from simple function that happens in decoding and encoding pipeline. Please refer to the paper for more details on these two workloads. So now I'm going to present our evaluation. We did all of our evaluation in Gem 5 Full System Simulator, and we simulate the PIM logic, both PIM core and PIM accelerator in Gem 5. And here's the detail of our system configuration. To analyze the PIM benefits, we basically study each of those targets in isolation and try to emulate them separately and run them in our simulator. Here I'm showing you the energy result across different workloads for three baseline: the CPU only baseline, the PIM core, and the PIM accelerator. Now that the result is normalized to the CPU only. So the first key observation we made here was that both PIM core and PIM accelerator significantly reduced the energy across all of the workloads. And the majority of this energy reduction comes from the fact that moving these functions to PIM could significantly reduce the data movement. For example, in text retiling in Chrome and packing in TensorFlow, we observed that getting rid of data movement contributes to 77% and 82% of the energy reduction. The second key observation we made here is that some of these functions, like text retiling, are extremely data intensive, and as a result, going from PIM core to PIM accelerator does not provide significant energy reduction. That's because some of these functions are data intensive and doesn't have much computational going on. And as a result, going from a general purpose core to a fixed function logic does not provide significant energy reduction. Here I'm showing you the normalized runtime result across all of the workloads for the same tree baseline. The result here is normalized to the CPU only. The first key observation here we made was offloading these kernels to the PIM logic, both PIM core and PIM accelerator, significantly improves performance on average by 44% and 54%. And the majority of this performance improvement comes from the fact that these kernels are data intensive and they can significantly benefit from the higher bandwidth and lower latency in 3D stacked memory. Similar to the energy result, we observed that some of these workload does not significantly benefit from PIM accelerator, or basically going from the PIM core to PIM accelerator does not provide a significant reduction into the runtime. But for other workloads like compression, you can see that going from PIM core to PIM accelerator could actually significantly improve the performance. So to wrap up, we stated that the energy consumption is a major challenge in consumer devices. And to figure out the major sources of energy consumption, we take a look at the widely used Google consumer workloads. We make two key observations from this analysis. We first observe that data movement is a major contributor to the total system energy, and we also observe that the majority of that data movement come from simple function that has simple operation. We show that we can use processing in memory to significantly reduce the data movement, and our analysis shows that offloading these functions to processing in memory to PIM could reduce the energy on average by 55% and reduce the execution time by 54%. Please refer to our ASPAS 2018 paper for more details on this work. Thank you so much.